just to wrap the point about the Bayesian optimization. So as I mentioned in the beginning, we always need to have a function that we want to optimize. So, and one of the biggest practical challenges in using the Bayesian optimization in experimental settings is figuring out how to construct these functions out of observation. So if, for example, if we measure mechanical properties and that's what we want to optimize, that we don't need to bother. But if we measure images and spectra, then figuring out how to create the optimization function can be non-trivial. So that being said, there are ways of, there are Bayesian optimization methods which are called multi-objective optimization. So multi-objective optimization means that you try to optimize more than one function at the same time, so kind of several. And what you try to discover is the Pareto front between the possible functions. For example, imagine that you want to make a material that combines stability and photoluminescence intensity. So in this case, you synthesize a large number of these materials. So all of them have some combination of intensity and stability. So, however, for some materials, you can improve both PL intensity and stability. This is called not Pareto optimal material. And for some materials, if you improve the intensity, then you will lose in stability. And if you improve the stability, then you will lose in intensity. So the points for which it is impossible to improve one of the functions without sacrificing the other one are called the Pareto optimal, and the goal, the kind of the surface on which this points lay is called Pareto frontier, and the Bayesian optimization that aims to magnify them, optimize them jointly, called multi-objective Bayesian optimization. So there are several ways of doing it. So it's called there are multiple ways of doing it. That's called the multi-objective B. We are not going to go into detail. So practically, the important thing about this multi-objective optimization is that it allows us to be a little bit more flexible about our hypothesis about what we want to optimize. So, for example, very often we say that we are not exactly sure what is that we need to optimize in order to achieve our final goal. So one of the ways to deal with this situation is to, oops, how did that happen? Way to, that's weird. I know how it happened. I didn't, it was in the previous presentation, so I cut and pasted without maintaining the style. So anyway, so one of the ways to deal with this type of situation is to say that, you know what, based on our long-term objective, we can formulate several possible objective functions, and then we try to optimize them jointly. So for example, if we want to improve the resolution in electron microscopy, we can say that one possible definition of resolution is the presence of the peaks in the k-space, so the information limit. Another is the contrast. And we can say that these two functions form two independent optimization functions. We can run the active learning experiment that tries to optimize both of them at the same time. And then we can actually figure out whether our guess was right or not based on the shape of the Pareto frontier. So if different rewards bring us to the same point in the parameter space, that means that our reward is robust. So different definition brings us to the same answer. That's good. If the Pareto frontier is extended, that means that if we optimize this reward, then this one is kind of sacrificed. If we optimize this reward, then this one is sacrificed. So in this case, they kind of lead to the different outcomes. So it turned out that practically playing with the multiple definition for the reward functions actually allows us to build more effective algorithms. And sort of this is the example of the multi-objective Bayesian optimization running on the electron microscope trying to optimize the resolution. So if you have the auto script, a way to control your instrument, so do get in touch. and we can make the things happen. So this being said, this is part of the things that are useful to know about the Bayesian optimization. There are obviously a lot of other things. So, for example, in some cases, we can use the results of the Bayesian optimization to combine the measurements by different methods. So this is called the multi-fidelity or multitask Bayesian optimization. So the typical example would be that we have the same parameter space. We can either run the model or run the experiment, and we want to figure out how to kind of jointly optimize them. This can be done, and how to use the knowledge from the model to improve the navigation of the experimental data set. So all these things are doable. All of them come with the requirement to understand the connection between the different parameter spaces, because the out-of-the-box models would use a simple correlation with terms, and practically it makes sense to use more complex models. But by now, between the automated tools and the existing platforms for code writing, this type of things are relatively easy to prototype, and they can be implemented for the real experiment. So practical experience that my group had over the last 8 years, first in Oak Ridge and then at UT, was that if you want to build something like this, always start with investing time and effort into the digital twin or the pre-acquired data set that allows you to prototype these models before going to the real instrument. So in all cases where we tried to develop an algorithm and deploy it on the instrument, immediately we had to go back and build the digital twin, because we spent a lot of time and money not understanding what goes on. In all cases, when we first built the digital twin, things worked more often rather than not, and the simulation results were a big part of the hyperparameter tuning. But anyway, we can always talk more about it, and feel free to get in touch with me to discuss the specific cases. But now, for the session before lunch, let me talk about more complex type of Bayesian optimization, which is called the deep kernel learning. Now, let me start with the motivation. The motivation was that, okay, imagine that there is a COVID for half a year. Nobody can go to the lab, and we can only prototype the code and machine learning workflows. And finally, the restrictions are partially lifted. So we can go to the lab, at least one person, and set up the experiment. And by that time, we developed the workflows for running the GPBO for the exploration of the image places. So the process itself was kind of difficult, because the first time you do something like this, the difficult part is to building the connection from the instrument and the control computer. But at that time at Oak Ridge, we had a way to do that. We got the DGX2 box, which was interesting because the microscope cost $300K and the box cost $500,000. So we set up this system. And then we run an experiment where this is the ground truth, and this is the active measurement campaign. So what we wanted to do is to measure this function in the image plane more effectively than just sampling everywhere. So image, in some sense, is a two-dimensional target function. We want to measure the hysteresis loop area. This is what we get. This is our answer. So if we compare this answer to the ground truth, it's actually not terribly bad. Like, we got correctly the concentration of the signal in this and this region. But now imagine that I come to my manager, and then I said, we just spent half a year of our time and $500,000 to get this image instead of this image. So that's not terribly impressive, right? It's kind of sounds like you guys spend a lot of time and money, and the result that you got is suboptimal. So what's the idea? The idea was that, in fact, we were solving the wrong problem. Because Bayesian optimization, or the simple GP where your surrogate function is defined over the 2D space, is great for problems like imaging optimization, exploration of combinatorial libraries and so on and so forth, because your target function is actually fairly smooth over the parameter space. And therefore, you can find it much more effectively than doing measurements over the grid. If we try to use the Gaussian process over the space like this, you see there are a lot of small details here, right? So the small detail practically means that the kernel length has become very small. If the kernel length is small, then there is no advantage of Gaussian process active learning compared to the grid-based measurement. There is just none. It's in fact it's more complicated because normal microscope scan like this. This is very effective scan pattern. It's easy to realize. It is almost optimal sampling for the unknown property. If we start to sample like this, first of all, most microscopes don't like it. Secondly, as Yanis showed, this type of scanning comes with the accumulation of errors, so we kind of start to have the jitter in the image. So in other words, it is a very stupid thing to do. There is no need to do it. However, what is important is that we realize that we were solving the wrong problem, because practically we don't have the problem of finding the image. So almost always the standard rectangular scanning is close to optimal. It can be improved, and both our groups and several groups in Europe worked on better scanning patterns. But for ideal microscope and fully unknown sample, rectangular sampling is optimal. The rectangular sampling become non-optimal for the cases when we have a complex scanner, like small scanner that can act over some part of the image, and the bigger scanner that can work over different part of the image. It becomes optimal if we know something about the image in advance, like use a low resolution scan in order to create a high resolution scan. Then we can do better. But if we don't know anything about the image, the rectangular scanner is optimal. But our task is also not to scan the image. Our task is to learn the structure-property relationship. And this is where the deep kernel learning comes into play. So let me first show you how it looks like, and then I'll show you how to use it. So the deep kernel learning is basically the hybrid of two things that we have already introduced. So one of this is the convolutional network, or general encoder. So you start with the high-dimensional input, and then you create a network that compresses it down to the latent variables. And then on top of this latent space, you run a Gaussian process that builds the relationship between the latent variables and the target function. So in principle, you can get almost the same result if you combine the variational autoencoder and the Bayesian optimization over the latent space. There are subtle details why it is not the optimal approach. But in this case, they are combined, and basically this system is trained at the same time. So you present the examples of inputs and targets, and then you train the Gaussian process and the network at the same time. So where does it come into play? So imagine that you do the following experiment. So you have the image. So in this case, it's scanning tunneling microscopy. So what you see under the microscope is some interesting objects. So there are some blobs, there are some holes, there are some patterns that look like this, there are some patterns that look like this. Obviously, it can be any other image. Scanning probe, PFM, electron microscopy, what's not. Now imagine that you want to measure the spectroscopy. And let's say at location A, your spectrum looks like this. In location B, your spectrum looks like this. So ultimately, what you want to do is you want to learn the structure-property relationship, meaning the relationship between the local structure and the local property. So structure is the type of object that you see, the local kind of motif. And the properties is the local spectral curve. So how can we do that? Way number one is that we make our decision based on what we see in the image plane. So for example, we find all the defects that have this type of geometry, and then we take measurements on this type of defects and in some of them, and if we get the reproducibly that all of them have this type of curves, then we can stop. Then we run the measurements for this type of defect, this type of defects, and so on and so forth. So this is a forward measurement. But at the same time, sometimes we have the inverse measurement. So for example, imagine that we want to find all microstructural elements where we have this type of peak. So notice the difference. In one case, in the beginning of the experiment, we have access to the image. We already have it. We need to choose the locations for the detailed study. In one case, we define in advance what features in the image space we're interested in, somehow rank them based on the priority, and do measurements only in this location. In the other case, we say that this is what we care about in the spectral measurement, and then we want to discover what structural elements have or maximize this property. The first type of experiment can be done by human by point and click, and can be automated by some form of the simple policy decision making using some form of image recognition. The second type of experiment is a learning experiment, so humans cannot do it. So humans can only do measurements on the grid and then analyze results everywhere. So let me show you another example. So same type of problem appears for things like plasmonic measurements. So imagine that this is our nanoparticles that we see in the image. We can take the EEL spectrum. So by now you know that this is the zero loss peak. This is just the elastically scattered electrons. This is the H plasmon. This is the bulk plasmon. So let's assume that we want to find the region where this peak is maximal or this peak is maximal, or even something more complex like the ratio of these two peaks. So third example can apply for pretty much everything else. So we can do the same type of logic for this stem as long as we create a function that we care about. So how can this process happen? So the starting point in this case, we have a full image. So this is usually something that we can get very fast. So then we can split the image into the patches. So we can split the image into the patches based on the just uniform sliding grid, or we can find individual atoms and center patches on the atom. So the second would be far more effective for atomically resolved stuff. So, but anyway, we want to do it. So then once we created the image and the patches, we take the seed measurements at several locations. So imagine that this is our full image plane. So the image split into patches. So each pixel on this image is basically the center of the patch, and we have access to the patch. And then we measured the spectrum at the center of several patches. So patches are available everywhere inside the image, and the spectra are available only for several seed patches. Make sense? So just initial measurement. So what we do is then we take what we have at this page is the collection of all image patches. We have created them. They just come from image. We have a small number of the pairs between the image patch and spectrum. So small practically is remarkably small. So in many cases, this type of algorithm works if you initialize it with 10 points. They're remarkably robust, kind of interesting. So what you do in this case is you use this pairs of patches and spectra as the training set, and you train the deep kernel model that takes patches as input and produces the scalarizer of a spectrum as the output. So meaning that in principle, you can predict the whole spectrum, but it's much more efficient to predict the scalarizer. You train this model, and once the model is trained, you can apply this model for all remaining patches. So what we've done, we created a surrogate model that builds the relationship between the patch and the spectrum. And then once this model is trained, we apply it to all patches. When we apply it to all patches, that for all points, for all unmeasured points, we have prediction and uncertainty. We have prediction because this is the configuration of our model, We have uncertainty because this is the Gaussian process on top of the latent variable. So now, if in any special location we have the prediction and uncertainty, we follow exactly the same logic as the Bayesian optimization. We construct the acquisition function sort of any way we want, as the example, the upper confidence bound. And once we constructed this acquisition function, we simply choose the argmax of this function to make the next measurement. So this is very, very simple, at least if you've done it for 5 years. And the idea is that in this case, you basically build the probabilistic model that relates local microstructure to your property. And then once this model is built, you dynamically apply it over the space of possible microstructures. So trying to do something like this over the XY space of possible coordinates doesn't bring anything useful, because our expressive language for the functions over XY space is not sufficiently rich. But what we do is, rather than XY space of coordinates, we use the space of microstructures which are tethered to the spatial locations, and over the space of the microstructures we can do things much more effectively. So the thing which is cool is that fundamentally this problem is very similar to the problem of things like discovering the molecules with the right properties and so on and so forth, because at this level that's almost the same. And this is how the deep kernel learning workflow works. So we start with acquiring structural data, then we measure spectrum, then we define a scalarizer. So this is a very important step because it defines what physics we are interested in. We train the deep kernel model. We introduce the policy to balance exploration and exploitation. So whether we want to explore or maximize. Argmax give us next location, then we take the measurement, and then we kind of continue until we run out of the experimental budget. So the important thing here is the scalarizer. This is what creates the reward from whatever we measure. And experimental trace, this is a collection of patches and spectra acquired during the experiment. So the important thing which allows you to do a lot of cool things is that we can actually collect spectra, not only scalarizer. So there are many cool things we can do about it. So this is the example of how it works. So this was done when I was still in Oak Ridge, work with Kevin. So this is a new material, so flaky manganese PS3 material. So in some locations we have the eel spectra that look like red one. In other locations we have spectra that run like blue one. So we define the scalarizer. So in this case we say that we take the spectrum, we fit it by 2 Gaussian peaks, and then our scalarizer is the ratio of this peak to this peak. So the reason for doing it is that we wanted to discover the edge phonons, but practically we wanted to see what works and it doesn't. So this is probably the first truly automated experiment on the electron microscope anywhere in the world. So this is the flake. The red dots are the locations where the instrument takes measurement. And this is the evolution of our acquisition function. And you see that our experiment nicely focused on these regions, but it sort of ignores the rest of the material, and especially it ignores the whole. So we experimented. So this is what we have done. So this is our schematic. And this is what happens if you run the experiment on the several different flakes. And immediately you start to see things that are kind of interesting. So for example, we definitely know that the algorithm explores the edges. Makes perfect sense because we look at the ratio of the edge plasmon peak to the bulk plasmon. But there is a but. And the but is that here it explores this edge, but not this edge or this edge. Here, for whatever reason, it really likes these regions where there is almost corners, but not this type of region. Here, it explored the locations, but it never really locked on specific point. And here it liked this edge, but not this edge. So in some sense, it almost looks like that our algorithm is sort of smarter than we are. We provide a very coarse estimate of what the reward function is, and somehow it tells us that based on the criteria that we formulated, our sample is much more complex than we anticipated. So the this function is maximizing some locations, but not other locations, and we don't know why. So that was super interesting. And just to make sure that things work, we can define a different reward function. So for example, if we just look for the maximum intensity of this plasmon, you can see that now we are exploring the whole flake, but not the regions outside and not the edges. So in this case, if we choose the simpler criterion, then the exploration pathway becomes much simpler. So this is actually kind of not bad. So now, 5 years later, we understand what goes on and how to take advantage of it, but at that time, that was a surprise. Now, interestingly enough, we can obviously project this type of experiment on everything that we've done with objective rewards and so on. So objective was to understand the emergence of nanoplasmonic behaviors. The reward was minimizing the uncertainty in structure-property relationship. So in other words, can we predict yield from chip structure and optimize specific feature? The value is expected reward. This is the scalarizer. So that's what we measure. Action is the position probe at the given location, but the location is defined by microstructure. So technically, it's going to the right part of the microstructural space. State is image patch. Policy is myopic optimization. So we can do the same type of things for other measurements. So this is an example of the same type of logic for the 4D stem. So we can run the 4D stem experiments when we take data, analyze it in real time, and then we place the beam where we want to be, or we can use the deep kernel learning in the same way when we define the scalarizer, for example, the center of mass or asymmetry or whatever, and then we tell our microscope to explore the region. So you can see that it explores several locations. Now it kind of zoomed in on here. So practically, it is possible to do a little bit of the tracing of why it decided to do that. So for experiment, we have the image, acquisition function, prediction, uncertainty. So we can see how all of these functions change as the function of time. But we started to realize that for this type of experiment, a big problem becomes how do we define the reward function. So simplest example, the reward function in EELS is relatively easy to define, and it's relatively reliable because we understand what the spectrum means relatively well. For 4D stem, our measure signal is very complicated, but the reward function that we extract out of it is very primitive. It's just center of mass. And then we started to realize that the more complex the data, but the simpler is the reward function, the more the algorithms start to show weird behaviors or ladder straight. For example, if we run the exploration of the graphene using the center of mass of 4D stem, for few steps, it explored reasonably well. So you see that it sampled sufficient variety of the objects. But then the algorithm got stuck either in this location or in this location. So it really doesn't want to explore. And this location parenthetically is just the hole. So there's nothing interesting going on here. So, and we did this type of experiments for a long, long time. So first in Oak Ridge, then once I moved to UT, in the first half a year, we set up the deep kernel learning setup on the SPM. So it kind of works as well. And the problem was always the same, that once we run the experiment, if the experimental framework is simple, then algorithms work well. So this is the case where we discover the areas where the hysteresis loops open up. So under some conditions, for one scalarizer, we find the ferroelectric wall. For other conditions, we discover the ferroelastic wall. But if the rewards are more complex, then algorithms start to work weird. So it's possible to build upon this type of component, to build upon it. For example, one of the great things about scanning probe microscope is that you have multiple information channels. So as I mentioned, there is a difference between FPM and STEM, because in STEM, very often we have access to the basic image channel, which is our ADAPT image, and then we can choose which of the spectroscopies to take. So this is a kind of bandit problem. In scanning probe microscope, we typically have multiple parallel channels. So it's not a bandit problem because we acquire all the data at the same time. But at the same time, if we build any kind of decision-making algorithm, we need to choose which of the channels uses the primary channel. And some of the things that we can do is we can build the deep kernel learning models. When there are 4 channels, we have 4 models that runs on each individual channel, and then we make this model's prediction by this model to compete to determine which one gets to define the final experiment. So the same logic as in the structural hypothesis learning, but applied for the experimental data sets. So that allows us to build the understanding which of the channel is most predictive of the certain functionality. But again, we have the same type of problem that the experiment almost sometimes seems like it starts to fail, sometimes it definitely fails when the algorithm gets stuck in the specific location. So here you see that we explored multiple locations, and then for whatever reason, algorithm decided that this is a good point. We don't know exactly why, but at least here you can speculate that there is a specific topological defect. But in this case, it clearly wants to stick in these 2 locations. And if we look at the whole acquisition function surface, it looks like it's fairly uniform. So we don't know why it's happening. And that brought us to the point that we definitely made a step compared to the normal fixed policy experiments, but this step is not enough. So basically, we learned how to cast the microscopy experiment as optimization problem. So practically, we have humans sitting in front of the microscope doing stuff and selecting what to study. In this case, we casted the optimization framework, meaning that we are no longer limited by human speed. We can run the experiment at the intrinsic speed of the microscope, and we can also run it much longer. So the typical experimental campaign that we run now on the SPM somewhere between 10-20 hours. So imagine that it was your job sitting in front of the microscope and do the same type of things. We would be happy to do the same thing for the electron microscope, but we have to pay a lot for the time, and it's faster, so we can run the experiments considerably faster than that. But now in the conventional microscopy experiment, human runs everything. So define scans, position probe, define parameters, and so on. Long and slow process. In this simple version of the automated experiment, we define the reward function and policy before the experiment, and then we let it read. And very often what we see is that the initial several measurements, whatever 10, 20, maybe 100, are exploring broad part of the sample space, so we like that, and then things get stuck. And then we started to think about what may be happening in this case and realized that the best analogy here is driving a car. So imagine that you have a car, you're on the road, you choose the direction, you press the accelerator, and then you drive only straight. So if you choose the direction well, meaning you chose the right reward function, and if the road is straight, you can get very far. If your chosen direction is a little bit off, or the road curves, you will get off the road very fast. The same thing happens here. So we define the reward function and policies, but we have no certainty that they are correct in the long run. So that was interesting, and that was also the time when there was almost a peak of the situation that AI is going to kill us all because of the alignment issues. And we started to realize that running the experiments where we define the reward function and then just follow the experiment with the same reward function maybe not the right way of doing it. So maybe it's a kind of start, but it's definitely not the full way forward. So that was actually the first patent that I filed when I moved to UT. And the idea was very straightforward, that we have this decision-making loop of the active learning and for the deep kernel learning. So we can expand it by defining initial exploration targets. So this is our seed locations. And in fact, we can we can define them very efficiently. We define the physics that we're interested in. That's our definition of scalarizer. We define the balance between exploration and exploitation. And then what we decided is that we absolutely don't have to keep these elements constant. In other words, I can start the experiment by defining what I'm interested in. But while the experiment runs, based on whatever considerations, I can identify other objects that I also think are interested, kind of manual intervention. I can run the experiment using the defined reward function, but then I can look at the screen, decide that I don't like how the results look like, and I can change the definition of the reward function dynamically during the experiment. Or I can decide to shift the balance between exploration and exploitation. Then you can ask the question, how comes we can do that and the general machine learning community doesn't do that all the time? And the answer is very straightforward. You see, it all matters. What is your baseline, right? What do you start from? Until now, all the experiments that we are running for microscopies are human-driven. As the result, everybody who runs the microscope, meaning human operators, have the culture of deciding whether they're measuring interesting things or not. So we always have the human baseline and human comparison. The only thing about the machine learning is that it can work much faster, which means that human does not assess the result of the single step done by machine learning algorithms. Human assesses the results of 100 steps done by machine learning. So practically, this can be incorporated in many different ways. So we can calculate the full workflows, we can calculate the counterfactual, sort of a little bit along the lines of what if then. But basically, what we can do is to create the framework for this human-on-the-loop experiment. And there are several observables or monitoring signals that we have. So first of all, as I mentioned, if to build this type of algorithm is always a good idea to start with the pre-acquired data. Simply because the number of iterations that you have to build this type of workflows is usually in hundreds before you get something that is ready to be deployed on the real instrument. To be fair, this approach has a limitation. So about 3 years ago, when we started to work on this type of things seriously, we realized that for problems like structure property discovery in EELs, we are oversampled by about a factor of 100. So what I mean by that is that imagine that you take a data set where you take 100 by 100 EELs measurements. So this is pretty difficult. So EELs usually can be fairly destructive and time consuming. So this type of data sets usually have a lot of distortion. But imagine that you have this data set. Imagine that your measure of knowledge is the predictive uncertainty of the structure property relationship, meaning how well can you predict EEL spectrum given the local microstructure. It's a kind of mathematized object that can be extracted from your data set. And now let's assume that you have the full data set, which is 10,000 measurements, and let's assume that you want to define what is the minimal number of measurements you can take in order to learn this predictive uncertainty to be within 10% of the ground truth answer. And it turns out that you can, if you play your active experimental campaign correctly in terms of cheat points and the active steps, you can basically get this type of predictive uncertainty with just 1% of points. And that was actually amazing because it basically tells us that if we come up with a mathematically rigorous definition of the useful knowledge that we extract from experiment, then if we go from static measurements on the grid to the dynamic measurements by active learning, we can get 90% of the answer in just 1% of the experimental budget. So this is not an unassailable position. So if the measurements are done on the grid, they're much easier to visualize. They're much more amenable to the human perception. That's absolutely true. It is also possible that the useful physical information is contained in this 10% that we didn't measure, that we didn't know. That's also true. So we can argue about this type of definition. That's why I'm happy that so many of you are here, because we can get answers to this type of questions only when we have a community that creates solid benchmarks and solid standards. But the initial impact was that if we try to do kind of more or less rigorous estimates, we really can get things done at 1% of the time. So what we decided to about it is to be a little bit more serious about the calibration of the process. So, and another thing that kind of follows from that, that if our active learning processes are so efficient that we can learn the answer in 1% of the time, that means that we need to have much larger data sets for the benchmarking, because we basically run out of the useful data within the first 100 steps of the active learning experiment. That was a little bit disappointing, but the way it looked up is that we always monitor the improvement of our target function, and the way that we saw things develop is that we very rapidly go to maximum, and then the functions start to slowly decay. And the reason why it happens is because we are running out of the useful patches. So we already discovered the region where the function takes maximizes the value that we want to optimize. So anyway, going back to the monitoring of the automated experiment. So if I have a car and I want to steer it on the road, I need to have some feedback about based on what I'm going to steer it. So one thing that we can monitor is what we call the learning curve. So we can formulate our acquisition function. We can see how this acquisition function changes as the function of time. But since the acquisition function is determined at each spatial location, we can also calculate the dispersion. So look at these three scenarios. So this is the acquisition function when we just try to minimize the predictive uncertainty. So you see it's relatively smooth, and the width of this gray interval is very narrow because we basically explore all the pixels, all the different type of pixels equally. This is the example where our acquisition function is the expected improvement. Notice that it actually decays fairly slow, and it's very noisy, and this width is fairly broad. So this means that this function is actually fairly greedy. It explores only specific type of the domains, of the patches, and then everything else remains unexplored, and therefore uncertainty is large. It also illustrates that greedy methods remarkably don't work very well. So most of the time you really want to be exploratory more than greedy. This is the upper confidence bound, which kind of behaves somewhere between this one and this one. So another thing that we can visualize is the real-time, real space trajectory. So depending on what type of acquisition function we choose. So for the simulated data set, you see that this one explores the edges of the patch of particles, and for whatever reason, this region. Different acquisition function will explore the edges and then the regions inside this double layer. The third type will explore the edges and for whatever reason again find something unusual in this one. So then you can ask a question, can we somehow systematize what type of the microstructures does our algorithm explore? And the answer is very straightforward, right? I've shown you the example of how we use the variational autoencoders. So if we take all the patches in the system and dump them into the variational autoencoder, then we will get the latent distribution and latent representation of the microstructure. So each microstructure becomes equivalent to the point, some point in the latent space. So obviously when you construct the latent spaces, you need to pay attention to how good is the reconstruction loss. So for example, these are the patches. This is the latent space. You can clearly see that in this case, the reconstruction loss is very high. So our latent space captures the things like edges or the presence of the double layers based on intensity. So these are double edges. These are the edges between the double layer and single layer. These are the edges between the single layer and the empty space. It sort of learned how to identify corners, but of course it doesn't capture the much smaller details. So it doesn't have a sufficient expressive power. But once we've done it, we can basically represent the exploration trajectory as the motion inside of this latent space of the system. So in this case, I didn't show the time dynamics. I showed only the sequence of points for the different sampling, but it's relatively straightforward to run the same type of experiment and show where they will converge inside the latent space of the system. So in other words, one algorithm shows you, one type of representation shows you how your function is optimized, so when you reach the maximum, and this algorithm shows you where are you in the feature space of the system, meaning which features correspond to the maximum of this function. So this is basically how you do that, and this is how you can build the human in the loop type of interface. So this is, I mean, we cannot show you it on the real instrument, but this is a video that was taken about a year and a half running on the Spectra, where the human operator looks at the golden something that runs the 10 experiments, then looks at the experimental trajectory, so you see what has been sampled. Then human can dynamically redefine the reward function, say that I'm interested in the different type of the features, and continue the experiment for the different reward function or different balance of the exploration exploitation. So where are we overall? So for the time being, virtually all instruments in the world are run by humans. So that means that human sits in front of the microscope, human looks at the images and spectral data, and human issues the basic commands that are sent to the instrument. So practically that means that it is you and you and you and you looking at the screen and figuring out what to do next. And what you do depends very much on your experience. So the difference between someone like Andy or Gerd, who has been in the field for 30 years, and second-year student, is that second-year student generally knows what nodes to turn. But the person who has a much longer experience have a much better idea about what the outcomes will be and what nodes to turn to optimize things faster. That's what makes you a professional. But in all cases, you are limited by the human reaction speed. So humans can introduce commands to the instruments sort of once a second, optimistically, even though when I look at my kids playing Doom or Mario Kart or whatever, I think that can be kind of dropped to 1/3 of the second at least. But still, it is much slower than intrinsic microscope operation rate. So what the addition of the optimization workflow? So notice that when we made this diagram about 3 years ago, we referred to it as machine learning agent. So practically by now, agent is something else. But let's say this is the simplest agent, which is just optimization loop. So once we have it, then our ML agent has access to the imaging and spectral data, and the agent sends the primitive commands. And what the human does is that human, of course, can take over the control, but generally we expect human to tune the behavior of the machine learning agent by changing rewards or policies. And the value proposition here is that machine learning agent can operate at the intrinsic limit of the instrument operation, which can be many orders of magnitude higher than human. So we thought initially that we are kind of in the situation when we go from driving driving Toyota to driving Lamborghini, but then we realized that this is more like changing from the riding a horse to driving a car, because the goal is the same, go from point A to point B, but the way that you interact with the system is totally different. And the interesting thing that's happening now, kind of like literally over the last year or so, is that we can start to integrate this type of setting with the LLMs and agentic system. So as we discussed, letting the LLM to run the instrument is not a very good idea. I mean, it can work at some point. You can tell it find a small particle, whatever, but LLMs are not mathematized. So in all cases, when the LLMs and reasoning system produces the tangible outcomes, they were interacting with some form of the support language. Like if LLM involves the Python code, it works well. If LLM tries to count the number of R's in strawberry without the Python code, not really. Success of LLMs in mathematics was enabled by the fact that LLMs interact with the formal source language like Kalinin, and that allows LLMs to do what they're good at, making guesses, and they lean in order to formalize it. So if we want to have the LLMs running on the tools, we will have to have this type of formal support structure that runs on the instruments. And this support structure, at least a very big fraction of the support structures, is actually optimization workflow. So there may be others, and there are probably others, but for the time being, this is the setup that works remarkably well. So let's stop here, and after lunch, we'll talk about the non-myopic decision making, but I will be happy to take several questions if as they are. Questions? Sure.
So, in your notebook, the one slide you mentioned, that
it may be DKL model or the any predictive model that gives you probabilistic action. So simplest ones are the optimization loops that define the action in some low-dimensional parameter space. Can be something more complicated. But as I said, when I made this diagram, there were no agents in the sense of the modern-day agents. Therefore, so let it also be agent, but a small one. Sure, go ahead.
Can you hear me? Okay. When you're running the deep kernel learning, and you're having a neural network and embeddings that help to translate better speed, physical properties that you're trying to measure. Have you run into situations in the past where the embedding that your models have learned are really not at all relevant to what you're measuring? How difficult is it to get a model like that to converge properly?
That's actually kind of the big advantage. So the deep kernel learning creates the embeddings that are optimized towards a certain target, which means that they would be less good for a different target. VAEs define the universal embedding that depend only on structures but not on properties at all. So the result, they're good as the starting point, but they are not optimal for any specific application. So we didn't do it for the experiment simply because we don't have enough data, but we run this type of things for the QM9 datasets for modeling for molecules. We did this type of things for the processing trajectories, and DKLs, in all cases, DKL builds optimal embedding for specific target. Go ahead.
You were talking about this updating reward policy, like things like during the experiment. So I was wondering about like the human intervention. So how does it like practically work? Like usually, like do you let the experiment run and then update it, or can you intervene in between? And
you can do it between. So you can run experiment for several steps, and you don't like the result. So you can say that I want to redefine the reward function this way. So the ways that you can do it, you can have a collection of the reward functions and we choose it. You can have a reward function that have a tunable parameters. For example, you can have a, if your reward function is intensity in some spectral window, you can just change the spectral window. Or you can talk to your favorite LLM model and say that I want to create a reward function that does this and this. Please write the code that will calculate this reward function, and then you can substitute the reward function. So the important thing is that no matter what you do, it is a safe procedure because you change only the definition of reward function. They don't affect anything done on the instrument control plane. The only important thing is that you need to be able to estimate the effect of this change, because you see a reward function is your guess about what is that you have to optimize to get to your goal. But you personally make a judgment when you run it. You make a judgment whether you are confident with this goal or not, which basically means that you make one step up in the hierarchy of the reward function. So very often, if you look or try to analyze the human decision making, you can figure out that humans are driven by very simple logic. For example, if our exploration is limited to some part of the image space, we don't like it. We intuitively feel that exploration should be more broad. But it may be localized here because that's the location where something interesting is actually happening. So our judgment is very subjective, and I mean, it's natural, kind of all the microscopists I know will make this type of decision, but it's also subjective. It doesn't have a deep physical thinking behind it. So the fact is that for the time being, we are all very good in running our instruments, but our decision making is typically very, very shallow. So we start to understand the data much later than the data has been acquired. During decision making, we typically all create some form of very efficient shortcut. Like, I don't want to see this type of things because this is a noise fix due to this effect, or I expect my behavior to be like this and this is different, and therefore I change stuff. So this is a great opportunity for things like agents or more complex machine learning frameworks to be applied, because they actually can do that. I mean, the process will take time. It would be very, very interesting. But the starting point is being able to deploy the optimization algorithm, because unless we learn how to use the full dynamic range of our instruments, we are stuck to doing things slowly, and then we don't have any kind of progress.